Hello, everybody. Thank you for joining us on our fourth day of our British Science Week events that we have going on. Hello to those who've returned, and thank you for coming back. And hello to the new people who've joined us, especially for today. This afternoon, we have the pleasure of welcoming Dr. Maria Alfredsson, who's here to talk us about printed flexible batteries for sensor applications. I'm sure it's bound to be an exciting talk and about talking about what the work that she's doing, innovating for the future. As before Maria starts, just a reminder, please pop any questions as they come through, pop them down the bottom in either the Q&A box or the chat box if you want, and I will pick them up at the end and pose them to Dr. Alfredsson, and we'll get into a bit of discussion after that. But for now, I'll pass over to you, Maria. Over to you. Thank you very much.
Yeah, thank you. So just a bit of a background. I'm a chemist by training, or materials chemist. I started off as a theoretical chemist, so far away from where you would actually expect any innovation happening at all. So this is just an idea that you can actually change your route over the years and you can follow your dreams. And I think that is important, especially if you are in your early career and you don't know exactly where it is taking you. So I'm going to show you two examples of where innovation has come into my research. It's two very different projects. One is a slow research focused and research based project, and the other one is product driven because it has industrial funding. And you will see the time frame and the ideas behind it and how we are solving and we are approaching the problems are different. So it's still innovation projects, but the time frame and the way we are approaching it, I hope that will come out that they are different. So please come back and ask me questions about that one later on. But they are both based on the same idea, and that is that we are going to print flexible batteries for sensor applications. And I have a slide here that I showed yesterday, and I will go through that one during the evening. And it started off by that what we really wanted to do as a research project was to print flexible batteries. They should be integrated with an antenna, and that is so that we can transmit signals. So in this case, we have, and I will come back to it a little bit more, it was a quite simple sensor. It's a temperature sensor inside this package here. I think I tried to show it. It's a black little square there. That is a sensor, and that was measuring temperature. And then that information, the temperature, should be transmitted. And for doing that, we need a power source, a battery. So our first prototype here was to make a battery which had an integrated battery in it. And the aim of it is that they should sit on your body. So for example, is an ECG cycle here, and you just transmit it without having wires attached to you. That is what we were aiming for. And for that, it needs to be flexible, they need to be stretchable. And you probably know what a coin cell look like now and so on. And I will come back to it, but that was the aim of our project. So for coming to all these things, you need to know a little bit about batteries. So I think you know all where you find batteries. Most batteries are primary batteries, and they would be used at in toys, remote controls, Xbox controllers, and they are about 1.5 voltage. And this is how they look like. Most of them are AA batteries. But the original AA batteries, they wasn't as neat as that at all. they would look something like this. This is the first battery that you probably all heard about. That is a voltaic pipe. The principle is the same, but it's a big and it's very bulky. And the same with the Daniel cells, the Dunn cells, all these ones that was the first batteries that was produced. They were big and bulky and very heavy. So something needed to be done, and research and development and innovation made them smaller. And today we have an alkaline battery that is the size that you would have at home and you know about. We also have coin cells, of course, and I come back to that. So that is where we are today. But where do we want to be in the future? We want to have something like this. The bottom one here, which looks like two forks that are put together, that is actually a 3D printed battery. I'm not going to speak about that one today, but that is another thing we are interested in. And then we have these ones that are completely flexible, and I hope you can see you can bend those batteries. And that is where we want to go, because that would allow us to do printed electronics. So for example, I'm sure you have seen these flexible watches, and now you have this screens on your phones which you can extend, and that needs to have a flexible electronics, a flexible battery, and that is where we want to go. The other revolution was that we needed to have batteries that cannot just work once, like these ones, the primary batteries, the alkaline batteries that you have most of them around. Not all of them, some of them are rechargeable, but most of them, you use them once and then you recycle them, I hope. This other type is the innovation, was that we wanted to have batteries that we can use several times over and over again. And that is where secondary batteries come in. And the most common secondary batteries that you're probably used to are the so-called lithium-ion batteries. And they are the one that got the Nobel Prize in 2019. But that was after many years of research, I should have say. So there was a lot of research coming into it, and they started not actually to be produced until in the beginning of the 1991, when Sony made a first battery. But before that, we had recyclable batteries, this huge big one you find in Warwick Castle. And the first cars that was actually produced were electric cars. So having electrical cars, which we are trying to do today, they are not completely novel. The first cars were running on rechargeable batteries, like this big bulky batteries here. So that is interesting, but it's not only in cars we want to have these lithium-ion batteries. We want to charge our phone. We want to use our phone over and over again. So and the other thing is these smartwatches, so wearable material, but not only wearable watches, but we have a lot of wearable and smart electronics around, and we want to use secondary batteries. So that is something that we are also interested in. And then we are trying to combine these two ideas, a flexible battery and rechargeable. So this is some pictures I got from the electronics department, and some of them I've found also online. So this would be how flexible electronics, the current state of flexible electronics with the battery today. You can see we have the, this is the electronics. It sits on a flexible substrate, and this big bulky thing here, or here, that's your battery. The same here. This is actually something that is done over at EDA by Professor Batchelor's and Dr. Robert Horn's group. And you can see the battery here is big and bulky. It's not very flexible. So this is where we came in and what we wanted to do. So before I just go in to our contribution, I'm just going to tell you a little bit how a battery works, because that will help explaining the steps we have been going through on our journey. So this is a material, and I will see, I think I have to change the mouse, because otherwise it will not allow me. So when a battery works, what we are doing is that we are transporting ions from the anode, the negative side, to the positive side. And when that is happening, the light bulb lights up. When you charge your battery, so then you're taking the lithium back, and you can repeat this one thousands of times. When we are doing a battery, we don't measure if the lamp is lighting up or not. We are trying to follow it in an electrochemical cycle. So we will get a pathway or a curve that looks like this. It's called a polarization or voltage curve. And you can see that the voltage of the battery changes where the lithium is in the cell. So now we're charging the battery, the voltage is going up. We are using the battery, the voltage is going down. So that is the idea with the battery. How a battery is made in our lab, the old traditional way is, and I will see if we can move this window so that I'm not covering. We have material that is used on the negative side, the anode, that is carbon, just graphite and carbon black. And on the positive side, we have an oxide. This is nickel manganese oxide, and then we mix it with carbon black so that it's becoming electronically conducting. We put it in something called a ball mill, and we then ball mill it so that the two different components, the binder and the active material, is starting to stick together. And we run it for some time. When it is finished, we I will see if I can. We will mix it with a binder called PVDF. We have a solvent NMP, and that will give us a solution. And then we add that solution with the carbon black and the graphite, which we had in the ball mill. And that is a paint, it's a pigment. And then we cast that pigment onto a current collector. In this case, it's actually the aluminium that you saw before was the cathode, the positive, and the copper that I have here is the anode. This is the carbon. The carbon is on the anode and the oxide is on the cathode. You have a separator, which is a plastic, so that's not very good for the environment. We have copper and we have an aluminium tub, and then we sandwich them, so anode, polymer, cathode, and then we put them in a vacuum sealed bag, like a coffee bag like this, and then you get a battery like this. And this type of batteries are called pouch cells. And this pouch cell is small, thin, flexible, and you can see that you can bend it, you can put it around your wrist, and the light does not go off. So this would be a traditional standard battery that you find in car batteries and in a lot of other applications in your phones, laptops, and so on. The problem with this battery is that you can't control where that paint is going. And if you want to put the battery together with an electronic circuit, you need to put it down in a very special way. So we have to find other ways of casting that pigment. So you can use inkjet printing, just what you have in your printers at home. We can do something called screen printing, and you might know screen printing from hobby craft and so on. You can also do flexographic printing, and you will recognize that when you are printing labels and gift wrappings and all this, and crisp packaging and coffee packaging, that would be flexographic printing, and we can use that to print batteries, and that is what we are aiming for in our research. So the big question we got, and this is project number 1, was how can we get a battery containing a metallic current collector to be fully integrated with an antenna? Antennas do not like to add conducting materials like metals into them. So we were asked this question by the group in EDA who worked with antennas, and we said, that is the 1 million question. This was in 2012 or in 2011, but it's a long time ago, 10 years ago. So we sat down and we thought, we need to take away the metal. Conducting polymers can conduct both ions and they can conduct electricity. So let's go for that. That should work. So we started to work on removing the current collector, replacing it with these conducting polymers. So that was our solution to it. Now we had to try to find a way of doing it. So we had a student called Adrian Amig that was just starting at the time, and we asked him to go and find all possible commercial conducting polymers he could find and test them in batteries. So that is what he did. He went away, we did some analysis on them, and we found out that these conducting polymers that had a sulfur in them, they seemed to work better in the batteries. And there was two polymers that we found more interesting. One was called P.PEG, and the other one is P.PSS. The P.PEG has this group called, which is a P dot here, and it has its sulfur here. If you can see, I will see if I can. I'm not going to go into the chemistry of this, but there is a sulfur, and then what we have here is a long chain, which is the PEG. And PEG has been used for a long time in lithium-ion batteries because it can conduct lithium. So we thought, now we have something that is conducting electricity, which is the P dot. We have something that conducts the ions. That should work fine. And then there was P.PSS. Here you have a sulfur group in your P dot, and then you have a sulfur group here in the PSS as well. And that should also be interesting because it's charged, it's electrically conducting, and it is readily available because that is what you have when you are printing LEDs and a lot of electronic circuits. So those were the two we decided to go for. Then we got the PhD student working on this, and he was a theoretical person. So he tried to understand which of these two was best and why it was the best solution. Now we are in 2017, so we have gone 2 years forward. We look at the P.PSS, he did some simulations on it, and you can see what is happening. We have huge big phase transform separations. So the blue ones and the red ones, they do not like to sit together. They want to separate out. They don't mingle exactly with each other. We found a paper in 2015 that actually showed that that was happening experimentally as well. So that meant that we could trust our simulations. But the simulations we did was on the P.PEG, because we thought at that point that that should be a more interesting solution, because we had the PEG that could conduct the lithium, and this one here should move, but yeah, I'm sorry, that is the P dot PSS, and what we find is that the lithium likes to sit with this sulfate group, so it's actually a very stable solution, but it can move. And then we increase the concentration of the lithium ions and the salt and the negative ions here, and we could see that what happens is that the ions are starting to pairing, and that is exactly what we expected as well, and that means that the conductivity is going down. So we need to find a balance between how much salt we are putting into these polymers, and we calculate the conductivity of them, and that is important because we said that they are going to replace the current collectors. And this is just the conductivity for the ions. And to our surprise, what we found was that the PEG that we thought was going to be the part that was conducting the ions the most, because it should be a higher, the highest number, the higher conductivity. And you can see they are very, very small, but it is the experimental values. This is exactly what we were expecting. And you can see that the PEG is in the -12, and the P dot itself, if we take only pure P dot, is -11. So this is a small number, but it's bigger than this number here. And if we take the P dot PEG, which is the mix of the two, the co-block polymer, what we do find is that it's just in between. So P dot was actually the more advanced and the more exciting than PEG. So from that one, we decided, let's go back to P dot PSS instead, because that one is used in electronics. So from this study, actually what we found was that the P dot PEG was probably not as good as the P dot PSS. So this is when we started to think of the antenna and how the antenna should look like, and how we could now take this information and put it into this antenna. So there was a design by the same student that had done the calculations on the lithium, and he came up with a design of an antenna. He made this antenna and he put it at a lot of different substrates, so MDF, PVC, copper, and on the skin. And then he measured, and what he found was that the antenna worked when it was put on skin, and it works slightly different if it was put directly on the skin or if it was sitting about 2.3 millimeters from the skin, and that is exactly what we expected. So that was very positive, and that meant that we had materials for the battery, we had a design for the antenna. Now we just had to integrate those two and put them together. This is where his PhD finished. So two other students took this project on board, and now we are in 2018. And they did manage to put the battery together with the antenna and make a fully integrated battery. And what they did, if you look at the antenna here, can you see that that is actually copper? So I said before, you can't have a metal in an antenna, but your antenna itself is a metal. It's in this case copper. So they were clever, and they said, let's use the antenna as our current collector. So that is what we did. We printed this polymer P.PSS that we had found directly onto the copper. And then we merged it with the cathode on the other side, making sure that the antenna was not affected by it. And that was quite a tricky thing. But they came up with this solution, and then they measured, and they could see that this antenna that has this temperature sensor can we have a read range of about 7 meters, which was over our expectations. We didn't think we were going to get that, but this proved that we could do a 2D printed material that was fully integrated with the antenna. And this was a prototype, our absolute first prototype, not very professionally done. And this one is done in an open mylar, just so that you can see the design, but still a lot of more works to do, but it proved the concept. After that, we then started to try to optimize the performance of this battery. This is now just shortly after in 2018. And we printed this battery, the P.PSS, using a lot of different techniques. We used the Dr. Blade, which is the one I showed you in the first video, where we coated a thick layer of paint directly onto the current collector, which was the antenna. We also used spray coating, which is just what you would use at home when you are spray coating. And then we took an inkjet printer, just a normal printer that you have at home. We rebuilt it slightly, and we printed the battery with that. And we found that these inkjet printed batteries, they worked much better. And what I ask you to look at here is the number here in this corner. This blue line here goes above 200, and that is the inkjet printed materials. And that is about twice as high as the red and the green, which is the Dr. Blade and the spray coat ones. And that tells you the capacity of your battery. So how much power or how long your battery is going to last. So a normal carbon coated battery that I showed you before has about 400. These ones are about 200. So they are lower, but we have proved the concept that it worked, and that the inkjet printed, the manufacturing technique was important. Now we needed to scale up. We wanted to do this in the normal one, and what we found was that it didn't work. Our screen printed batteries, which is these orange lines here, they actually did not work. So we were at the crossroad, and this is where I think industry and academia is different. With an industry, you would say, okay, let's move on, change the material, go on, or go and contact a research department and say, can you please find out what is going wrong? We are academia. We ask the question, why is it not working? Because one of our research outcomes is publications. And for that, we need to understand why it is not working. And that is the difference between innovation in industry and academia. And you can also see the timeline to get here has been very long. I have taken it from almost 10 years now. And that was to come that it didn't work. I would say that maybe, there are other ways. The crossroads might not always be just 2 ways. We might get other crossroads. And in the future, and with a little bit of imagination, we might introduce more dimensions. So the crossroads might not be the stop, and not always just to say, move on, or why is it not working? But I think that it's different. That is the difference between industry and academia. We have moved on. We have decided that we needed to make the electrolyte, not from a liquid as it is in normal electrolytes, but we needed to make a flexible printable battery. So we have introduced a solid state battery, which you can see here is completely stretchable, and it is flexible. So we can now put that together with our P.PSS they were not very good in printing, but you can see they can create freestanding films, which are completely flexible, and we can put them in a battery, which is flexible, you can see here, and very thin. So it didn't stop us, it just took us aback a little bit. And we have decided that we then have to start doing different developments. So we are looking at different materials development. So we have changed the material from PDOT, for example, and we have played with this binder to try to get materials that works better. And then we moved to the cathode side instead. And we found another use of this PDOT PSS. We use that as a binder. And that is, so materials development is going forward and we are getting that. It's just a very slow, a much slower process. So it's working, but it's slower. Finally, I'm just going to show you very, very quickly another project that we have had. And that project is driven by industry. So they came to us and said, you have 9 months to develop a new battery completely from scratch, and it has to go in production in 9 months. So we started off from something called TRL, which is technical readiness level of about 0, and we have to go into production in July. The other thing was that they wanted a battery that can go over 2 voltage. And the problem is that it has to run on water, and water breaks down at 1.7 volt. So that is not going to, they don't go hand in hand. So again, a challenge. And here we came with another solution, and that is that we worked with something that is called water in salt. We changed the properties of electrolyte. So we added loads of salt, so very, very high concentration of salt, and that allowed us to make a battery that actually goes above 2 volt, actually 2.3 in this picture, but we have done it about 2.5, 2.6, we have changed it. And the idea behind it, not exactly this, but the idea by these water batteries is very simple. This would be a battery that is just run on normal sodium chloride, so the table salt that you have at home. So this is a water, and then I will speed up a little bit because we are running over time. What is happening is that we just take salt, and what you can see when we add salt is that the light bulb starts to lit up, and if we add more salt, you get stronger light. And that is how an aqueous battery would work. What it does need is, sorry, I'm going to stop this one, and I'm going to move to the next slide. It's my, okay. So yeah, so I'm sorry here, I'm just, what we did show that was that we could take a battery and we could start it with water. This is where we are now, about 5 months or 4 months in. We have a battery that we can start with water. And what happens is that the ions are moving from one side to the other when we add water. And this is our battery that is running on just pure water, tap water. And you can see it's lighting up this red LED. And why do you want to have a battery that runs on water? So these batteries are supposedly going into these lateral flow tests. Some of the lateral flow tests that you have seen are for COVID-19. I'm sure that those are the ones that everybody is seeing now. But if you put the battery into these lateral flow tests, they need to be stored for really long time. They can't have a self-charge. They can't be an expiring date like normal battery. That is why we want to start them with water. They also need to be safe for storage and safe for transport. Lithium-ion batteries that you have, that is the problem we have today, that we want to produce car batteries in the UK, but we can't transport lithium-ion batteries through the tunnels and on flights. So we need to make the batteries in the UK. And the thing with these ones is, of course, that you don't need electricity to charge the batteries, but you can use the battery over and over again. Just add more water and they start. And that is the end of my presentation. I just wanted to thank everybody that has been involved. So Matteo and Sally has done a lot of the battery work, and then the EDA group, Professor John Batchelor, Robert Horn, and Christina Kakarami. And then, of course, the financial support from Mologic, EPSRC, DSDL, Alistor, and Beamtime for SRF and DLS. Thank you very much for listening.
Thank you very much, Maria. I'm clapping on behalf of the audience. Thank you for those who have already asked questions. Please pop any other questions in, stick them in the chat to me or in Q&A if you wish, and I'll pick them up. That was a fascinating talk, Maria. Really genuinely interesting, such a diversity of different things that you covered. I had one question here, but I'm not sure if you covered or if someone had missed the point was missed a little bit, but it said, which was how much salt would you need to power like a light bulb for a long period of time? When you showed the video with the salt going in.
Yes, yes, that is a very good question. It's actually not the amount of salt that you are adding in. It's as long as you have the water there. So So
would you need to replace the water all the time instead?
Yes, you do. It's the water you need to replace. So let me go back because I had to go do this very quickly. So the idea with these salt in water batteries is that if you dissolve a very low concentration of salt, so for example, if you're cooking pasta or potatoes, you would add a tablespoon of salt in a big pan of water. That means that the ions that are dissolving into the water will be surrounded by water molecules. And that allows the water to break down when you put electricity across. In this water in salt, what you do is that you put in a saturated amount of salt. You put in so much salt that you cannot dissolve any more salt. And that means that the ions are no longer going to be surrounded by water molecule. They are going to form these ion pairs that I said we could see in the first simulations with the polymers. So if I go back here, back to the beginning of our journey here, you can see that there is a clustering of the ions together. And by having that clustering of ions, they protect each other so that they don't break down the water as easily. So for these batteries, we have a concentration of 21 molar of the salt. LiTFSI is the salt that I used as an example here. It's not necessarily only that we have used, but that is the first example that was published. And we do add about 21 molar. So it's huge concentration of salt. But
yeah, for those who don't know what a molar is in the audience, 21 molar is a large amount, a high concentration of salt to use. So, yeah.
Yes, I didn't calculate how many atoms it is. I am sorry, but it is a very large amount. So for example, if you were putting, yes, it's weight percent. I can't remember how. or the weight percentage. So the thing is that it's also increasing the volume. So when you add this salt into, because you increase the volume by twice about, that is how much water you are putting, salt you are putting in.
Wow. So going back to your analogy of boiling your potatoes, you'd certainly have a heart attack if you boiled your potatoes in that amount.
Oh yes, you would.
Yeah, absolutely. So building out that, I have two questions that we had here related to that. I don't know which one to go first. So you showed your simulations. How do you perform? We had a question about kind of how do you perform these? Is it just a big computer essentially, or how is that done? What do you need to make that happen?
So yes, so these calculations here that I showed, they were done on a Linux cluster that we have in the university called Tor. So some of you might have heard about the computer Tor. It was the first generation of Tor we used, because that is the one that we had in my group at the time. So that one had at the time 52 nodes. So we had 52 times 8 processors. Nowadays, we would like to do these at bigger calculations, of course, and we have repeated some of them, and then we have used supercomputers. So really the big computers up in Edinburgh, which is the UK supercomputers. So these boxes here, I can't remember how many thousand of atoms they had, but we have repeated it with bigger simulations using millions of atoms.
And I guess the question from that is, why do you perform a simulation as opposed to an experiment?
It's a good question. 2 reasons. One is that we want to understand what is actually happening on an atomistic level. And this is a good way of finding out really what is happening, because it can be very difficult to interpret experimental results. That is one of the reasons. The other reason behind this project was that we wanted to identify if which one of these polymers that was most suitable for the batteries, which one was going to have the highest diffusion, highest conductivity, and so on, without having to investigate all the different compounds in the lab, because that is what we did with the first. We bought all the conducting polymers we could think of, and then we tested them. And some of them worked and some of them didn't work, but we didn't know why they worked. So in this project, it was really to try to figure out why some of them worked and some of them worked less well.
So we use the simulations to look at a much larger area than we could with an experiment. That makes sense. So moving back to we have a couple of questions here coming in around this kind of the flexible stuff and stuff you were talking about at the start. One question we have is, how do you increase the capacity of these flexible batteries without just making them bigger again?
That is a very good question. Changing the materials. That is one of the things we are doing. So the obvious way of increasing the capacity of a battery is to use more surface area or thicker electrodes. We are trying to do, the problem we are trying to do is, of course, we are trying to decrease the thickness of the battery. The other problem we have is that we are not having as much space as you would have in a car battery. For example, car batteries are really big. So there you would speak about kilograms when you add everything up. Here we are speaking about milligrams. It's really small. So we have to change the chemistry. We have to think about other materials that have higher capacity than are used in car batteries. And that is the exciting thing with this project as well. We can't follow what is always known in the field of lithium-ion batteries. Saying that, we don't always need as much power because it's driving electronics. So we don't need to have as high voltage. In a car battery, what you're trying to do is to get really high voltage, 4.5 volt and above. That is what we are driving for there. Here, 2 volt is fine. We start the electronics, but we want the battery to go for as long as possible. So we are looking at chemistry that maybe don't have as high voltage, but where we can increase the capacity instead. So we are a different balance.
Cool. So it seems the building again from this a little bit, and you talked a couple of times, and you showed those lovely videos of kind of printable things and the things when you were forming these on the surface. And I think if I remember the phrase quickly, you use like an inkjet printer, like someone would have at home. And so we've had a question from someone at home specifically asking this: is there going to be a time in the future when we will be able to print our own batteries using our printers?
Oh yes, absolutely. I think you can. I wouldn't be surprised at all. The problem with them is that different printers works with different things. So some printers work with aqueous-based inks, and other printers work with polymer-based inks or organic solvents. So you need to choose which printer you are working with. So we have both in the lab. And the other thing is that you can't just take something and try to print it, because it will clog your nozzle and your printer head. So you have to make your inks so that you can print them. But yes, absolutely. This is exactly what we are doing. We are working on developing these inks that you can use for printing your batteries at home. Absolutely. And this is exactly what a lot of our research are going on. What we are doing in the lab is that we don't have a huge, big inkjet printer that they would have in a manufacturing plant. So what we are doing is that we are taking what we have available to see how it works, and then we take it and we try to scale it up. And that is where we are now, and that is where quite often research in academia gets stopped. That is where we get stuck. We are getting there, and then we don't find anybody that are interested to scale it up, or we don't. So that is where we work with industry, because we can't scale it up without manufacturers. So
that I understand that completely. I have a question around that we had come in, but I'll come back to, I'm following out from the original question. I think I'll come to that first. I mean, it's super cool that you could, well, in the future, we might be able to print these at home. And you talked a lot about, having to make your own paints or make your own printing materials. And that triggers a question in someone's mind, which is that obviously, like, ink flakes off a thing, or when you print something, it rubs off and things like that. So are we going to be worried that in this future that we're going to have batteries failing, or are we going to be worried about, there's already problems of batteries heating up and exploding and things like that? Is it going to be worse with these flexible batteries? Or?
So no, absolutely not. So actually, one of the things I didn't speak about was all the mechanical tests that we are doing on them. So the print can't come off. And the thing is that the batteries work absolutely so poorly if you don't have good adhesion. So one of the thing we are really working on is to make sure that we get good adhesion. And the problem is that different substrate needs different binders to stick to the surface. And you probably know all this because you have wood glue, you have plastic glue, you have metallic glue, and so on. The same principle with this paint, so this glues, we have to change what we are printing on. So that, and we do test them, and we make sure that we have good adhesion. I think that answered that question.
No, that's perfect.
But I think that I'll follow up with the safety question then. And yes, absolutely. One of our worries is, of course, that there are runaway reactions that will heat up. There are two things with these batteries that we are developing. One is we don't use as high voltages as you would use in car batteries and in your mobile phone, because the mobile phone, the lithium ion batteries in your mobile phone are 3.2, 3.5 volts. We don't work with those high voltages. We work with lower voltages. The other thing is, and if I go back to here, the thing that is normally causing your runaway reactions is that your electrolyte, which is a liquid, causes some kind of a short circuit. And that is the electrolyte and the separator that is normally failing. In this case, what we are doing is that we are developing a solid state electrolyte, which is also used as your separator. So we are taking away that step that the electrolyte and the separator can fail. So this is much, much, much safer batteries. And that is, I didn't speak about safety, but of course, we want to have the batteries flexible and stretchable, but safety is absolutely crucial. There is another way we could make sure as well, and we thought about that one long, is that we know that there are things we can put on, there are fire retardant materials that can be coated on to substrates. So we can use that just as an extra safety thing, but we are not there yet. So, but of course, it's something we are very, very concerned about.
Fantastic. Thank you very much. So the last question, which came about, which you mentioned about industry coming in, and it brings us back to your last story. And I think this is probably, thank you for the questions from everyone who's put them in. They've been an interesting conversation. The last question that I have comes back to this, which was, you told this story about essentially in the 7-month timeline, we're going from nothing to having something that at least worked in theory, or you demonstrated working. How did you manage this compared to your previous story when in 7 years you've taken some iterative steps? Were you building on it? Was it an easy area of science, or how was this possible?
No, not easier at all. The thing is that normally when you are doing a research project, you are trying to also solve all the reasons behind things, why it doesn't work, why it is working. And this is where I'm saying that, so for example, when we came to that crossroad, if you were in industry, you would probably just say, now we are moving on, let's try something different. And I can tell you with this project, we did start something, we worked on it for 2 months, we couldn't get it to work. So we just had to say, this is not working, and we just had to completely change direction, because time was is of essence, because we still have to reach what we are expecting to reach. But we just had to change, and we had to take a step. Actually, we had to take quite a few steps back and rethink the whole idea, and forget about why it didn't work. But if it was a research project, we would say, we need to figure out why it doesn't work so we can publish, and so on. So just different approach, where the product is the main aim, while with the old ones, we are constantly trying to optimize and improve and so on.
So less time spent on understanding and more just finding like the route that works and following.
Yeah, exactly. Yeah.
Fantastic. Well, in that case, thank you very much to everyone who asked those questions. I think it made quite an interesting conversation. And thank you very much for attending today. And thank you very much again to Dr. Maria Alfredsson for spending an hour this afternoon talking to us about those things. For those who are interested, please do sign up tomorrow. We've got 2 more talks tomorrow at the end to finish our British Science Week. Otherwise, see you then. And thank you very much, everyone. And see you tomorrow. Have a lovely evening.